Moving into section 3, going to be covering hardware components. Now, there are 3 main components in a computer, and I'm sure you've heard of all these components if you've ever gone shopping for a laptop, starting with the brain. The brain of the computer is the CPU, Central Processing Unit. This is the main function of the computer, has all the operations, and it operates in a cycle of fetch, decode, execute. We'll come back to that concept in a couple of slides, but just think of the CPU as the max brain of the computer, and I'm sure you've heard of a couple of CPUs. Intel i7, I think we're up to i9 or like i11 now, I don't even know. But you can buy CPUs, either the main ones are Intel or Ryzen for brands, manufacturers, and the more latest version of a CPU, the better it's going to be. So if you buy an i5 Intel processor, it's going to be just slower, and it's not bad, but it'll also be cheaper if you're trying to save money than going out and buying the latest Intel CPU that they offer of like an i9 high CPU processor. So currently I'm operating on an i7. I bought my laptop back in 2022, and you can just save some money by going with i7 over i9. Or Ryzen is a bit cheaper manufacturer than Intel, because Intel is like the Mac of the world, and Ryzen is like, you know, the PCs. You're just buying a brand there, but some people are very particular for their CPUs that they buy. I'm just trying to give you an example of CPU. So again, this is the brain. When we think about how fast can the brain work, this is where memory comes into play. I'm sure you've heard of RAM or ROM. If you look up the specs on your computer, you can have anywhere from 2 to probably 16 gigabytes worth of RAM, again, going back to our conversation about bytes. And this allocation, this is random access memory, and this is saying how fast can your computer store the instructions so that the brain can output those instructions. So if you have 2 gigs of RAM, that is going to store less instructions at a time than 16 gigs would. This is, 8x the power of storage instructions that the memory can hold. So if you have more RAM sticks in your computer allocated to be able to store the instructions, let's say we had a program running here, a second one, a third one, and a fourth one. Well, if you have 16 gigs of RAM as composed to maybe like 2, you're able to feed into the brain more instructions at once. And then if you have a CPU that is, i5, it can process and fetch, decode, and execute all of the instructions coming from memory into the computer at the capacity of whatever the i5 specs are. But if it were an i9, it would process it faster than the i5. And there's a whole slew of information you can get lost into, but just defining the main core concepts of a computer, number 1 is the CPU, number 2 is the memory, and then over here we have input-output devices. And all of these work together to pretty much have your computer function. So, input-output devices. This can be anything that is sending an input or an output from your computer. And it's going to say, if I'm writing an essay and I make the input of hitting the A on a keyboard, well, I have now sent an input to my device. It's going to go to memory and then back to the CPU to then execute on my Word document an A. This all happens very, very fast, and you're dealing with multiple input and output devices at a time. And we'll come back to input-output devices in a couple of slides. But just be aware, 3 main components of a computer. We got the brain, we got the storage capacity and how fast it can store instructions to give to the brain, and input-output devices, which is basically telling your computer what to do at what time and feeding this kind of in a loop. Now, memory organization. This is a segment of memory that we have, and we can break it up into 5 different spaces. So the memory is what the computer uses to store instructions and data, and when you execute a program, the operating system can provide a portion of memory to have that process run. And the program's memory is broken into 5 parts here: stack, heap, BSS, data, and text. So starting with the stack, this is your memory that's used for non-static, your local variables that are explicitly declared in your program. It's managed by the CPU, and it's very fast access to all your variable data. The heap, number 2, this is used for dynamically allocated memory. And so if we put like static here, we can put dynamic here. And it's used for, okay, well, it's slower. So if we put fast over here, sorry, we'll put slower over here. And it can be allocated to the stack, and it can be allocated and freed as needed, which is why it's dynamic. So if you have a bunch of stuff coming in, this is going to be statically assigned, and this is going to be dynamically assigned. What's in here is called free space, and this is reserved memory that allows the stack and heap to grow into. That's why the arrow's here. The stack can become larger and build down if more static variables are being placed into memory to allow the program to run, or it can grow from the bottom here dynamically and grow up, and there's just a bit of wiggle room in here to have free space reserved for memory for the stack and heap to grow into. The third part of memory is BSS. This is holding uninitialized and zero initialized global and static variables, which kind of exist in the program. Section 4 here is the data. This holds non-zero initialized global and static variables within the program. So kind of this is initialized, this is zeros, and this is uninitialized, zeros for your variables. And the text section here is number 5, and this stores all of the compiled code of the current program that's running. So, are you ever going to get asked this on an exam? No. But do we want to figure out how memory organization is working? Yes. Should you be aware of how memory is kind of flowing in here? Yes. Maybe if I asked you to remember a couple of sections from memory, I would probably just focus on the stack and the heap section here, and remember that the stack is very fast and the heap is kind of slow, and stack is for static allocation of variables and the heap is for dynamic. But basically, this is your memory in a nutshell. So moving into a buffer overflow concept, this is going to be the first concept that we kind of discussed based on what we just learned in memory. So a buffer overflow is a type of security vulnerability in which a program writes more data to the buffer than it can hold. So if we think about our stack and heap that we just had, we're going to cover stack overflow in a second, but basically think about buffer overflow as putting in more data than the buffer can hold. So let's say we had a buffer, and we'll say it's 3 allocations deep for the buffer. If I try to write in a 4th segment here, it may push the buffer beyond what is supposed to be allocated for it, and it could overwrite section 3 with whatever I'm pushing into the buffer, whether that's my malicious code that I want to write and have execute or overflow the memory, it will kind of expand the buffer and overflow it so that maybe 3 is over here now, and 4 is taking up this space in the buffer now. It's overriding adjacent memory locations, and that can cause unexpected behavior such as a crash or the execution of malicious code, which we just talked about. Buffer overflows often occur when the program does not check the size of the input data and assumes that it will always fit within the buffer. So a good example of a story that I heard was a kid playing Xbox, and he didn't know the password to get into his account, as his parents had locked it out, and the password had only allocated, let's just say 16 characters in length for the buffer. Well, the kid just decided to button smash and go over 16 characters and cause it to just log in because it didn't verify the size of the input data, and it just overrid it, and the kid was able to log in through button smashing. And that's an example of a very simple buffer overflow where kid didn't even know he was doing it, but he just button smashed until the input validation wasn't being verified, and he was able to overwrite the buffer size and then log into the program. Buffer overflows are a common type of security vulnerability in the software, especially older and poorly written programs. And to prevent them, you should always validate the size of the input data and ensure it will fit within the buffer before storing it. Input validation, probably want to star that off, and if you're ever on OWASP or whatever vulnerability that comes out, it's always like, oh, input validation was the cause of this, not verifying it. I mean, sure, but it's a good way to properly manage it. It's just unrealistic to blame everything on poor input validation. But if you have input validation and those checks and bounds in place, that can definitely help you out. Another example of input validation that is more simplified is, let's say we're filling out a form online. And if we have, first name, last name, month, day, and year of our birthday, first name, last name, if I'm able to type in whatever I want, that's a less secure input validation than compared to if we had a drop-down menu. Because if we have a drop-down menu, well, I can only select options that are in the drop-down menu. So I'm not able to input anything that's not already validated by the drop-down menu. So the drop-down menu acts as a form of input validation to ensure the values that you're putting into the form are within the allocation to the values that the form wants. I'm sure you've seen this. Errors on form or inputting data incorrectly. It's all a form of input validation. So that's another just simple example there. Moving into a Stack Overflow. The goal is to exploit, it's a Stack Overflow exploit. You're going to overwrite the function return address or a function pointer in order to redirect a program to execute your malicious code. A Stack Overflow vulnerability, it's a type of buffer overflow, which we just talked about, where it takes advantage of how the stack is leveraged in memory, and it's dependent on the structure of the stack. So a new stack frame is created each time a program or subroutine is called within the computer, and the stack frame is a way to isolate the set of tasks from the other tasks. The stack, if we think of it as just stack 1 here, and then we have another stack for a different set of parameters or functions to execute, the stack needs to operate in what we call last in, first out. So if a new set of executions or parameters or functions comes into the stack, let's say that's number 3, this was the last stack added to the stack, and that means it needs to be the first one out to be executed. Number 2 and number 1 cannot be executed until number 3 leaves the stack and is executed by the computer. So when excess data is entered into one of these variables here, and we'll get to this in a second, this is called a no-op sled, stands for no operation, you could potentially overwrite the return address, which would have a placeholder for the next set of instructions to execute the next set of functions on the stack, and again, we're in memory. So it's pretty much like if this set of instructions executed, that's great. Then at the end of the program here, it will say, okay, go on to execute stack number 2. And then at the end of stack number 2, this address pointer would point to number 1, and it would work its way down the stack. So in most cases, a potential malicious actor would kind of fill in the local variable segment with a no-op sled, which in hexadecimal is 0x90, and this is just blank. It's going to do no operation for the computer, and it will build this no-op sled very high within the stack and leave just enough room before the return address for their malicious code to execute down here, if we had malicious shellcode or something. So the stack will read from top to bottom. It's going to read all this no ops. It's taking advantage of the stack, and then at the end of this function, maybe we had a return address that's going to be modified to then point to where your malicious code is written. So then once this no-op command executes, it will just lead into the malicious code. So again, we're working within the stack portion only here of memory. This is our free space, and if we're filling just the stack free space with a bunch of no-op sleds, and then until the end where we have our malicious code, we can alter this and take advantage of the stack to then execute arbitrary code or whatever we're trying to do. And it's doing that by overriding the return address or pointer to redirect the program to the code. So that's an example of stack overflow, pushing in blank values onto the stack until it's executing and then leading your return address pointer to your malicious code. Definitely encourage you to go take a look at buffer overflow attacks and specifically Stack Overflow. There's probably some videos out there that make the analogy that the stack is like a set of plates, and if you just push more and more onto the stack, you're going to overwrite all of the allocated buffer memory within here, and then pretty much go over the same concepts that we just discussed. So buffer overflow, that'll be something you want to know what it is, and probably would be a question on a Security Plus exam. Moving into the two types of system architecture, we have CISC and RISC. So CISC stands for Complex Instruction Set Computer. This is our basic software, our x86 designation here. So software for CISC, and then when we're talking about RISC, we're thinking about hardware and ARM-based architecture instead of x86. With CISC, this is going to do several low-level operations with one instruction, and this is, where our CISC architecture is found in computers. This is probably the laptop that you're working on. This is most servers in production environments. Any laptop you have, desktop computer, etc. It's probably based on CISC x86 architecture. When you go into RISC, this stands for Reduced Instruction Set Computer, and we're dealing with ARM architecture instead of x86. This is only one low-level operation per instruction, where this is several. And when we think of RISC-based architecture, we think of Android and tablets and our phones. And if you've ever gone out and downloaded like Kali or if you have a Raspberry Pi, or really just trying to download any VM at all, you need to make sure you're selecting the correct VM based on your system's architecture. You cannot run the ARM version of Kali if your laptop is running CISC architecture. That's why you need to select the appropriate installer or download package based on your computer's architecture. And I'm sure you'll see this more as the course goes on for denoting between CISC and RISC, but just be aware that most computers that we're talking about is CISC, and then just kind of like iPads and phones and Android devices, tablets, or operating systems, some Linux flavors. If you're going to run it on ARM-based architecture, we're going to be talking about RISC. All right, moving into the concept of multi-threading versus multi-processing. Probably going to give this one a star because it's just good to know and relevant to understand how your computer is able to multitask and multi-process. So starting with multi-threading, that is on the left here. This whole box is the CPU. So this is one big CPU, and this is another CPU, and this is another CPU. So we have three CPUs here. I'm just going to draw a line here for a second. Over here, this is multi-threading, and this is representing multi-processing. So starting with multi-threading, remember when we talked about the CPU, we had the cycle of fetch, decode, and execute. And that is how the computer, the brain of the computer, is executing your programs. So the first step is it's going to go out and fetch the next instruction. Remember that came from memory. And then after it fetches it from memory, because memory is what holds all those sets of instructions for the computer to say what to do next, it will then decode that set of instructions, and then it will execute it and perform whatever computer function it's trying to do, whether it's opening an application or running something. There's like a million different executions that are going on your CPU at a given time. If you have multi-threading, we'll kind of just call this one thread here. Fetch, decode, execute, that is the first thread. If we introduce another thread and then a third thread, the thread is representing the number of fetch, decode, execute cycles that it can do on one CPU. So multi-threading is fetching multiple threads at once from memory and performing all of these executions singularly on the CPU. So if it wasn't multi-threading, we would just have one fetch, decode, execute, and that would be our one thread. And then our next set of instructions would come in from memory, and that would be the next thread. But to be faster and more efficient, your CPU may be able to do multi-threading. So multi-threading would be doing multiple fetch, decode, and executes all simultaneously on the CPU. So that is multi-threading. When you go to purchase a CPU, you can see the capacities for how much multi-threading it can conduct. And obviously, if it has more multi-threading capabilities than a different CPU, it's going to be able to execute a lot of instructions faster than the other CPU. Over here on the right, we have multi-processing. So as the name suggests, we have multi-processors. So this is Central Processing Unit 1, and this is Central Processing 2. If we have two CPUs on our computer, but each of them are limited to one fetch, decode, and execute, and one fetch, decode, execute on our computer, but we have two CPUs, well, this might be similar to just having two threads open. But obviously that's not how it works, but multi-processing, that is multiple CPUs, whereas multi-threading, that is multiple threads within one CPU. Now, think about this concept a bit further. If we have multiple CPUs and each CPU can do multi-threading, you can get a very fast processor that's just executing multiple threads at once, or sorry, a very powerful system with multi, processing enabled. Maybe you have like 8 CPUs and they can all do whatever value for multi-threading, and you're off to the races. So obviously that comes with cost and capacity for your computer to be able to handle all of that processing power. But the CPU is pretty important, and obviously you would need more memory if you have more multi-threading or multi-processing going on. So it all scales up together based off of those, big 2 components of the computer. Talking about input-output interfaces and devices, these are what we talked about as that third component, the main component of the computer for our input-output devices that are going to, be something on a keyboard that presses a button. But input devices, this can be the mic that I'm talking into. I'm sending in audio as an input to my computer. I can input keystrokes. I can do mouse clicks. I can work with this pen that I'm drawing with. These are all input devices, and they're connected to your computer either through some sort of input interface, whether that's USB for your mouse. This looks like an Ethernet port for connection to internet, some video displays here, and if you're on Team Mac, you have your Thunderbolt ports. You have adapters if you want, like a HDMI type adaptation or input into your computer. Every computer comes with different interfaces that you should be aware of when trying to purchase a computer, so that you can try and match what function you want to have as an input for that computer. That if you're Team Mac, you're Thunderbolt, and you try and plug in a USB, Mac's going to charge you to go get that adapter to work with that one interface that they give you. Same for if you're trying to do an HDMI cord to plug in a monitor to your laptop to have an additional screen. Well, if your interface isn't there, your computer is not going to be able to take that as an input. Output devices can also vary. I can output audio as well in the form of speakers. I can output a piece of paper to a printer. I can output a display to another screen. There's so many to cover for input and output devices. I think they're very intuitive. You've just probably never heard them called I/O interfaces or stuff like that before. So anyways, whatever input-output device you have, you're going to buy the adapter, or make sure your computer has the capacity to take in or push out that device's signals that it's going to transmit to the computer and function correctly. Now, one more concept to touch on is the interrupt-driven input-output. And we have 2 sections here, interrupt and an exception. An exception goes further into, breaking things down into traps, faults, aborts. This is just something to be aware of. This is not going to be on a quiz or any exam, but just giving you a different example of an interrupt that can be triggered by an input-output device, i.e. hardware. I'm sure you've pressed Control-Alt-Delete on your computer. That would bring up an interrupt triggered by the hardware of your keyboard to send an interrupt to your CPU to instruct your computer to stop what it is doing and follow that trigger of Control-Alt-Delete to interrupt your computer's operations. That was a hardware-driven interruption, and say, stop what you're doing, address my Control-Alt-Delete, and it trumps everything else because it's a form of a interrupt-driven input-output. An exception, going from hardware over to software. This is more for programming and error reporting, and it's triggered more by an execution series of events that's not preferred. So you can have traps in your software or program applications. You can have a fault. If you've ever had your calculator divide by 0, it'll give you the error message. Aborts for error reporting. I just wanted to give you an example of really an interrupt and how your computer can stop what it's doing based off of the input that you give it, and really drive your computer to do something else. Going back into memory for a second, we're going to be covering the different kind of priority schema of memory. So what's most important, what's most volatile towards what is kind of secondary and not as important. So starting at the top of the pyramid, we have our registers. This is registers and cache. These are the CPUs we had talked about, Intel and Ryzen, AMD. So this looks like it's an i7. If you have registers for memory, that's going to be stored in the brain, in the CPU, along with cache memory. Registers and cache, if you have those executions stored in your CPU, it doesn't need to go out and fetch, decode, and execute from memory over here. This is an example of DDR3 memory, a RAM stick, because it's stored in cache. So it's cached on the CPU. It saves it from having to go out and reach to the next best allocation of memory, number 3, at your primary memory storage of RAM. And cache will hold like your most recent activity. So let's say every time you open up Chrome and you go to Google, well, that's going to be cached in memory. It's not going to go out and perform DNS every time because that address to google.com has been cached and your computer is familiar with what you're trying to do. It will cache that instruction. It'll kind of just build from the stack, kind of top down, and say, this was most recently executed, so I stored it in cache, then the most next recently executed thing, and it will just push it down and your cache will fill up. So registers and cache and primary memory, again, when it goes out to fetch, it's going to go out to your gigs of RAM storage. Probably you have something from 2 to 16 gigs of RAM. Server grade of storage, we're pushing into the 32 gig range. And you're going out and fetching. This is where everything is storing for instructions to say what's next to execute by the CPU. And these 3 here are what we're going to introduce as a new term of volatile memory. That means if the computer loses power, you will not have the memory stored to be accessed at a later time. This becomes important in forensics and incident response when you're trying to figure out what happened on a computer. A lot of great data and insight comes from volatile memory. So now we keep our computers on until the investigation has completed, instead of pulling the cord on it and saying, we don't want the malware to spread, and we're only going to work with non-volatile data that remains even after the computer's power is lost. Volatile is very important. Anything actively running on the computer is going to be interswapping between the registers, cache, primary memory, CPU functions, etc. As soon as the computer loses power, that memory is volatile, so it went with the power and you cannot recover it. Moving into non-volatile data, this is where we talk about kind of secondary storage or secondary disks. So maybe you have an SSD drive or hard drive, a hard disk drive on your computer. We'll cover those, what they are in a second. But this is like your secondary memory. So where are you going to store all of your essays and Word documents and PowerPoints and photos and songs and stuff? You're going to store them on the secondary memory disk that's allocated to your computer. This will survive if your computer loses power. You turn it back on, all of your data is still there. And then kind of the 5th precedence of memory is this is going to be your external storage. So here we have a passport device that maybe you own, or like a USB stick. It could be a tape, a CD, that's external media. And all of this is obviously non-volatile, will survive a power outage from your device. And just kind of working down the precedence here for how important memory is and what is volatile and what is non-volatile. I would definitely know these terms and what they mean and what pieces of memory fall into them and which ones, kind of survive non-volatile, pulling the plug on the computer. talking about a solid state drive versus a hard disk drive. So, as we mentioned before, your computer is going to write everything in the form of ones and zeros. And this is an example of a magnetic disk that spins. This is storage in your computer for where it's going to write all of those ones and zeros. And the needle is going to move up and down. And if you remember, if we had our chart of how my brain works for electrical signals being sent to the computer to then impress or not impress onto the disk to write a 1 or 0, if it's writing to disk, I think it goes up as every allocation bit is set. So that's kind of the needle being applied to the disk, the needle not being applied, the needle pushing down, not pushing down. And this is very, very fast. If you've ever had an external storage device that's a hard disk drive and you've put your hand over it, maybe you feel it vibrating or something spinning in there, well, that's the magnetic disk, and that is how all of your data is being stored in the form of ones and zeros through the needle moving up and down and then in and out of the disk here. And then when your hard drive becomes full, all of this will have been written in the form of ones and zeros, and there's no more storage capacity. You know, when you delete devices, maybe it overwrites this section of the disk, or, you know, this line of the disk. That's a whole nother conversation we're not going to get into right now. But just be aware differences of having a hard disk drive. This is slower, it's cheaper, and it's very fragile. If you drop it, you can affect where the disk needle is being written. You could crack something. Whereas the more modern approach today and the more expensive option to purchase with your computer is the solid state drive. This is using non-mechanical parts here. It's like flash storage. So these are pretty much all groups of cells. Instead of having a big magnetic disk with a needle that moves up and down, your data is being written still in ones and zeros, but it's like flashing the memory through electrical signals. It's not as fragile as parts that can break over here if you drop it. It's more efficient. One of the biggest differences you'll notice when you buy a computer that has a solid state drive over a hard disk drive is how fast your computer can boot up, because it's not waiting for anything mechanical to spin up and power on and then, you know, start going to work. This is flash. It's fast. It's going to spin up within 3 minutes or so. So you should check the specs on your computer to see what kind of storage you've purchased. And then when you shop for your laptop, I would definitely recommend purchasing one that uses a solid state drive over a hard disk drive. So it's best for operating systems, gaming apps, frequently used files. Your computer may have both in there. It may have a larger, cheaper, maybe like terabyte hard disk storage, and then maybe like a 256 gig solid state drive that you can use as primary or secondary storage, etc. One of the last things we'll talk about is RAID, since we're talking about memory and storage. This stands for the Redundant Array of Independent Disks. When we think about RAID, all I need you to know right now is that there are 5 different types of RAID, 0, 1, 5, 6, and 10. And the biggest points to remember why we would use RAID is number 1, for redundancy of our data. In case we lose it, we have another copy. And number 2, performance. How fast can we provide data in the event of a failure, or provide an exact copy? So if we just take a look at RAID 1, it says it's using data mirroring to create an exact copy of data on 2 or more disks. In the event of a disk failure, the system can continue to operate using the data stored on the remaining disk. So let's say this is disk 1, and we have all this memory in here. If we want to have an exact copy, and this is, you know, A, B, C, D disk storage, we would have a 1-for-1 exact copy of A, B, C, and D on this disk over here, because it's mirroring an exact copy. So it has redundancy of data and performance, where if disk 1 fails, we now have a backed up disk redundant array of data written to these disks that is an exact mirror of how disk 1 looked. We're not going to go through all the RAID types. I don't think it's important for you to be aware of all the different, what's the difference between RAID 0 versus RAID 6. We'll get to that at a later time, or you can research that on your own. But definitely the term RAID, you should know what it stands for, and probably just these two things right here. And it's a way of increasing the way your disks are stored by making copies of them. And then basically these differ in how it's making copies and how many copies. That's all. So just a good term to know is RAID. With that, we've wrapped up Module 1 for Sections 1, 2, and 3. If you purchase the books for the course, that will be additional homework, quizzes, and content for you to review and really hone in on the concepts that you've learned in this mod.